that was constant volume. What if we don't have constant volume? What if we have constant pressure? Maybe this reaction's happening in a beaker, it's open to the atmosphere, then we have constant pressure. So we can get energy evolving as both heat and work. Most of the time, we're not interested in the work in chemistry, we're just interested in the heat. So we've got another term here called enthalpy. Enthalpy has the symbol H, and that is the sum of the internal energy and the product of its pressure and volume. So H, enthalpy, equals internal energy plus P times V. We're interested in the change in enthalpy. Enthalpy is a state function, doesn't matter how we get from one place to the other. So delta H is going to be delta E plus P times delta V. So we learned earlier that delta E was equal to Q plus W, and P delta V, that looks a lot like negative W, right? W is negative P delta V, so if I multiply both sides by -1, I get a negative W here, and the W's cancel each other out, and I get delta H is equal to Q at constant pressure. So the enthalpy change equals heat at constant pressure. Delta E and delta H, very similar in concept, often similar in their values, very easy to mix up. The exact difference is not that important for us, but delta E measures all the energy, both heat and work, that's exchanged with the surroundings, whereas delta H only measures the heat. The difference between these two is important when you have either a lot of gas, the volume of your reactants changing a lot, like maybe you had a lot of gas and it all reacted and the volume got really small, or your product volume is changing a lot. So maybe the products got really big compared to the reactants. So as long as we stay away from weird things like that, we're fine. I'm just going to skip this because it's not worth our brain power. It's not. So the signs of delta H and delta E follow the same convention. Delta H is positive when energy is coming into the system, like it's a positive when money comes into your account. It's negative when it goes out. When the energy, the heat comes in, that's called endothermic. So endo reminds me of the word into, and thermic refers to heat. So this is heat into, and when the heat is released, we can say heat exit, exothermic. So we have exothermic and endothermic. One is exit, one's into, the opposite of exit. We talked earlier about chemical hand warmers, those little pouches that have iron in them, and then when they're exposed to air, they oxidize, and it's an exothermic reaction, and it gives off heat to the surroundings. Your hands are the surroundings, and so you feel the heat. The reaction is releasing heat. The burning of natural gas is another exothermic reaction. The only good reason to burn natural gas is, to make heat, to do something else, right? So heat is given off. You can also have endothermic reactions, like the ones that occur in these instant cold packs that you might get in a first aid kit. And kind of like a light stick, there's a little pouch in there that you got to break, and you squish it around, and it starts to get cold. Do you ever stop and wonder, how does that happen? That's not something that we see happen every day, right? Things just suddenly getting cold. Well, this has ammonium nitrate in it, and as it dissolves in water, that's an endothermic process. It's taking heat in. Where does the heat come from? It comes from the surroundings, like your hands or your sprained ankle, right? And so your ankle becomes colder because the reaction is absorbing the heat. Any questions about that? We should be able to identify processes as being exothermic or endothermic. Sometimes it's a little bit tricky. It says identify each process as endothermic or exothermic and indicate the sign of delta H. So an ice cube melting. Do we have heat going in or heat going out? I'm getting conflicting. So one of the things, it's like, okay, we're not sure. What would we do to make the ice cube melt faster?
Add more heat.
Heat it up, right? So it must be endothermic. The heat's going in. So this is endothermic. And then what's the sign for delta H? Yeah, delta H is positive. Okay, nail polish remover quickly evaporating after it's accidentally spilled on the skin. Oh, look, nail polish remover. Oh, I accidentally spilled it on my hand. Wow, that's cold. I also spilled it on my iPad, which is not so cool. Shouldn't do that. My hand feels cold. What's going on here? So we have to ask ourselves, okay, what's the system? What's the surroundings? The system here, we're talking about the nail polish remover evaporating. I am not part of the nail polish remover evaporating. I am part of the system. My hand detected that it was losing heat, right? Another question you can ask yourself is, what could you do to make it evaporate faster? Add heat, right? So this one's also endothermic. And delta H is positive. Any questions? These questions can be really mind-twisting. Yeah.
Well, isn't your body warm making it evaporate, or?
Well, my body is warm. My body is providing the heat for it to evaporate. Yeah. But it's endothermic because the heat from my body is going into this process.
Oh, wait, okay, yeah.
Yeah. So you really have to, because there's always something gaining heat and losing heat. And so you have to make sure, which part of this thing am I talking about? Am I talking about the ice cube melting or my hand next to the ice cube that's melting? That would be different. Okay, gasoline burning within the cylinder of an automobile engine. Exothermic. Pretty much anytime you've got burning, combustion, this is going to be exothermic. So you go out in the morning and the engine of your car is the same temperature as everything around it, right? And you turn it on and you drive it to school. Should you open the hood and put your hand on the engine? No. Why not? It's really hot. You're going to get burned. Where'd all that heat come from? It came from the burning of the gasoline. And we weren't burning it just to heat up the engine, but we were losing heat when we were converting it into kinetic energy for the engine to move the car. So this is exothermic, and delta H then is going to be negative. So an exothermic reaction gives off thermal energy. Where does that come from? The internal energy of a substance is its kinetic energy plus its potential energy. Kinetic energy is related to the temperature of the object. I mean, we're not talking about physics here where balls rolling across floors. If it was coming from the kinetic energy, as the reaction gave off energy, what would happen to the temperature? It would go down because it's losing its kinetic energy, but that's not what happens. So it must be the potential energy. in a chemical reaction, the atoms are rearranging themselves. And so we are having bonds broken and bonds made. This has something to do, rewind. This is related to the positions of positive nuclei and negative electrons. And so when weak bonds are broken, that's going to absorb a small amount of energy. So in order to break a bond, you have to put energy, put effort into it to break it. Because of the law of conservation of energy, the reverse is that when you make the bond, it releases energy. Because you can't just be breaking and making bonds and creating or destroying energy. So breaking a bond requires energy. Forming a bond releases energy. So here, if we're breaking weak bonds, that absorbs a little bit of energy, and we're forming strong bonds, that's going to release a lot more energy. And so then the net result is that we have energy being given off from the reaction. In an endothermic reaction, the opposite is happening. We're breaking strong bonds, and we're forming weak bonds. And so the energy from the surroundings is being used to break those strong bonds. Questions? An endothermic reaction occurs in a flask. What happens to the temperature of the flask? It goes up, it goes down, or it doesn't change. So, what is the system we're talking about here? Is it the flask? No, it's the reaction. The reaction is in the flask. So what's happening with the reaction? Is it absorbing heat or releasing heat? It's absorbing because endothermic heat's going into the reaction, the system. If heat's going into the reaction, it's coming out of the surroundings. So would that make the temperature go up or down? It would go down, right? So the temperature falls. Those questions are simple but very confusing, right? You can just go in circles in your head. Sometimes it's helpful to write it down for yourself. So the enthalpy change for a chemical reaction, delta H, also known as enthalpy of reaction or heat of reaction. This is an extensive property. It depends on how much reactant reacts. So with the butane example, a little bit of butane burning, a little bit of energy. A lot of butane, a lot of energy. So just because they agreed to do this, we calculate delta H for the reaction in relationship to the balanced chemical equation given. And so we look at this balanced chemical equation, which we usually interpret in terms of moles of substances, right? So 1 mole of this and 5 moles of that. So we're going to say that this is the amount of heat exchanged when 1 mole of this burns, which is equivalent to 5 moles of that. It produces 3 moles of this and 4 moles of that. So this number can be related to moles of any of the reactants or products, which makes it a really great conversion factor. Consider the following thermochemical equation. We have 2 of A getting together, forming AA. And here's the heat of reaction. So 51 joules are released when 2 moles of A react. How much is going to be released when 6 moles react? How many times bigger is 6 than 2? 3 times bigger, right? So then the amount of energy must be 3 times bigger. So which of those numbers looks closest to 3 times 51? Well, it's not A or B, is it? It's not that one, it's not that one, it's one of these. Should it be negative or positive? It should be negative, just like this, because we're not changing anything else. We're just saying that there's more. Okay? More substance reacting, more energy. Ammonia reacts with oxygen according to this equation. Calculate the heat in joules associated with the complete reaction of 155 grams of ammonia. So here we have stoichiometry again. Stoichiometry is a big deal in general chemistry. So I've got 155 grams of ammonia, and they want to know the heat associated with that. So I can use my balanced chemical equation to help me organize my thoughts here. So 155 grams of that, and then I'm trying to find energy, and I guess I'll come over here and put a question mark in kilojoules. So what's the starting path for stoichiometry? Grams to moles to moles to grams. Grams to moles to moles to grams. Are we starting with grams? Yes. So grams of ammonia to moles of ammonia. Like, let's write that in here. Grams of ammonia to moles of ammonia. Are we going to grams? No, we're not. So we don't need grams at the end. We're trying to go to kilojoules. And this value relates directly to 4 moles of ammonia. So I don't need to go to moles of something else. I can skip that one, and I'm just going to go straight to kilojoules. So 155 grams of NH3, I'm going to convert that into moles of NH3. That's a 3. And then I'm going to use the heat of reaction, which relates to moles of those things in the reaction. So I'm just going to tell you that the molar mass of ammonia is 17.034. This is the part we're learning about. So it's negative 906 kilojoules for how many moles of ammonia? For 4. And yesterday I was going to tell him about this, and then I just did it instead. It's really easy to overlook dividing by the 4 at the end. And sure enough, that's what I did yesterday. Times negative 906 and divide by 4. Negative 2061.025 kilojoules. And we should have 3 significant figures. Negative 2.06 times 10 to the 3 kilojoules for burning that mass of ammonia. Any questions? One more example. What mass of butane in grams is necessary to produce 1.5 times 10 to the third kilojoules of heat? Second question, what mass of CO2 is produced? Okay, this is the number we're given, and let's do the first question first. Mass of butane in grams. So we're going to start with grams to moles to moles to grams. I am trying to find the mass in grams of the butane, and I've got energy, which I guess, I could write it down here. 1.5 times 10 to the 3 kilojoules of energy. Well, I'm not starting with grams, but I am ending with grams. And I need to get to moles of butane to get to the grams. And then somewhere, and I've got the kilojoules, I can go from kilojoules straight to moles of butane. And I don't need those. So 1.5 times 10 to the third kilojoules of heat. I'm going to convert that to moles of butane and then to grams of butane. So I want moles, no, I want kilojoules down here, and I want moles down there. So the moles cancel, and the kilojoules cancel, and everything's good. So the mole to kilojoule thing comes from delta H. So that's the number of kilojoules I did that. Negative 2658 for how many moles of butane? 1. And then we need the molar mass of butane. I'm just going to calculate that real quick. .12 is the mass of 1 mole of butane. So 1.5 times 10 to the 5th divided by negative 2658 times 58.12. And I'm going to get negative 327.9.9 grams. Which is wrong because I did 1.5 times 10 to the 5th, and it was times 10 to the 3rd. I thought that seemed awfully big. So, about 32.799 grams. Can we have a negative mass? No. What happened? Well, we have a sign on our heat of reaction. We didn't stop and think about what would be the sign of the heat here. We are producing this much energy. So from the point of view of the system, is that negative or positive? The system is putting out heat. So that's negative. So we should have had a negative sign there, and then we'll end up with a positive mass. And so we'll get 33 grams. Any questions?
Yeah, my brain's gonna not like this producing.
Yeah. Okay, does anybody want to see the second question? Or are your brains full?
My brain's full.
Full brain, yeah. If you want to see it, I did it yesterday.